Hello students, this is Mr. Maat with another physics lesson. In this lesson we will start with a new chapter, and the chapter is called sound. Well, you all know what sound is because you're communicating throughout the day with your parents or other students. You listen to music. Well, that is all based on sound. Well, we're going to figure out the theory behind sound. We will focus on vibrations, what is the source, what is the medium and what is the receiver. And we always do some calculations about the speed of sound. Well, in class I will show you a demonstration about the sound in a vacuum. And there is also some homework for next lesson. You just need to round off all the things for lesson 2.8.2. So make sure you do that. Most of it will be online, but all the other stuff you can just do in your digital reader. Well, first let's start with the definition of sound. And the definition of sound is like this. It's a vibration that propagates as a wave through a medium. So it actually tells you that it's some kind of a wave that travels, well, for instance, through air or through water, and it behaves like a wave. Okay, that's sound. You probably saw pictures like this before, and it's actually a representation of a sound wave. And it tells you a couple of things about the sound wave. So if you would record a sound wave with your phone, there are apps for that, you would get a picture that looks a bit like this. And the picture tells you a couple of things about the sound wave. First of all, it tells you something about how loud the sound is. So the size over here of the sound waves actually tells you how loud the sound is. Are the waves bigger? More sound. Smaller waves? Less sound. So that's one thing that you can tell about a sound wave, the volume. Well, the other thing that you can focus on is actually the pitch. It's how high or low the sound actually sounds. Is the sound higher? Then you have smaller waves, very close to each other. Other waves, very big waves, then you have a really low sound. So low sound, you have really big waves. Small sounds, well, the distance between those waves reduces, and then you get a higher tone. Okay, so we already know a few things about sound. But there are three main things that you need for a sound, otherwise you can't experience the sound. First of all, you need something that starts the vibration. Well, something that starts the vibration, we call that the source. And that can be everything. That can be my vocals, that can be just you smacking on a table. Something needs to start vibrating. Well, we call that the source. Well, of course, you need something to pick up the sound. Well, that are your ears, of course, but also a microphone or your cell phone can be used as a receiver. Well, in between the source and the receiver, there needs to be some kind of a medium. And the medium is just a word for, well, some kind of a substance that there needs to be. It can be a solid, it can be a liquid, it can be a gas, but it can't be a vacuum. And that's important to remember. So, for a sound, to hear the sound, you always need, well, actually molecules in between the source and the receiver. That's why in space there is actually no sound, because in space there is a vacuum, and without molecules there can't be any sound. So if you're standing really close to an astronaut in space and you shout through as hard as you can, well, the other won't hear you, because there are no air molecules. And the air molecules need to start vibrating, caused by the source. So, without those molecules, without the medium, no sound. Without the source, if there's nothing vibrating, no sound. If you don't have any ears, no sound. So, I already talked about a vibration. And the vibration is something that you need to remember. What is actually a vibration? Well, the definition of a vibration is this. It's a movement around a fixed point. So you need to make sure that you understand that it's actually about the movement of those molecules, but those molecules don't travel from this point on to your ears, for instance. They only vibrate. Yeah, so they are vibrating around a fixed point, so they always go back to that point. We also call that a to and fro movement. Well, over here I zoomed in on one of those air molecules or particles. Well, if there is no sound, that air molecule will be completely in rest, and we call that the neutral position. It won't move. Well, as soon as there is a sound wave, Well, the sound wave, of course, is going to hit this particle and the particle starts vibrating. Well, it starts vibrating, for instance, to position number A, and then it will automatically go back to its neutral position. Well, if it vibrates on, then it moves to position number B. Well, when it reaches position number B, it goes back to its neutral position. So you need to remember that the vibration is just a movement around a fixed point. In this case, the neutral position. Okay, but how does actually sound travels through a medium? Well, that has to do with all those molecules. The molecules, they bump into each other, and that's the way the sound actually travels. So if this is the neutral position of that particle, then the particle, of course, starts moving. Well, when it hits another particle, then this particle, of course, starts moving as well. So you see that in this way, actually the sound travels, well, through the medium. If the particles are very close to each other, we call that a certain name, and that is called high pressure. So when you're in a high pressure region, the molecules are very close to each other. There is a small distance between those molecules, actually almost no distance. So we call that high pressure. Well, the opposite can also occur, of course, and that is when the molecules are very far apart, and we call that low pressure. And there's a large distance between those two particles. So we have high pressure regions and low pressure regions. Okay, now let's start calculating some things. Well, you already knew that the formula to calculate the speed of something is equal to the distance divided by the time. Well, you always need to use standard units. So meters divided by seconds will give you meters per second. So we can actually calculate the speed of sound, for instance, through air or through water or any other substance. That doesn't matter. So in symbols, the formula looks like this. Lowercase v equals lowercase s divided by lowercase t. Well, you already saw that I showed you that there were some particles involved in a sound wave. Well, you can imagine that the closer the particles are together, the faster the sound wave will travel because there is just less distance to be covered. Well, we're going to do a calculation like that. We have this situation. I have the situation with air molecules. I have over here water molecules and molecules of steel. So we're actually going to send a sound signal through air, through water and through steel. Well, we're going to use the same distance, so every time the sound needs to travel 5,000 meters. So it travels 5,000 meters from the source up to the receiver in each situation. I also gave you the time that it took for the sound wave to travel that distance. Well, in the first situation it was 14.71. In the second situation it was 3.33 seconds. And over here it was 0.96 seconds. Well, I want you to calculate the speed of sound through those mediums. So please put the movie on pause for a minute and then I'll come back. Okay, let's first write down all the things that are given, of course. Well, all the things that are given are already over here. So that's my first part of ROPEC. My second part is to formulate the plan. V equals S divided by T. Well, I'm going to fill it in. 5,000 divided by 14.71. I will get an outcome of 3.4 times 10 to the power of 2 meters per second. So the speed of sound through air is approximately 340 meters per second. Well, let's see what happens if sound travels through water. Again, the water molecules are very close to each other, so probably the sound will travel faster. Well, you see that over here, with the same calculation, different values, you get an outcome of approximately 1,500 meters per second. So, for sure, it's traveling faster through water. Let's see if it travels faster through steel as well. Well, the air of the molecules are very close to each other over here. And look at this. Almost 19,000 kilometers per hour. I converted it into kilometers per hour just to give you an idea how fast actually the sound is traveling. So 19,000 kilometers per hour. It's huge. Okay, There is some homework for next lesson. Hopefully everything from this video was clear for you. If there are any questions, you can of course post them below this movie. Otherwise, thumbs up, and I'll see you next lesson. Thanks for watching.